And first of all, I'd like to thank the organizers and summit committee members for the kind invitation. And I'm okay. Well, except for 2 times in Saint-Flouré, this is my very first time in spending in France. So I'm enjoying the atmosphere in this area of France. So thank you very much. Okay. So I'd like to talk about about this topic. And actually, because of this particular part of the title, so in this by this title, I'm specifying the class of fractal to curves. So that might sound that certainly sounds disappointing, maybe. But so in the near future, hopefully near future, I'd like to improve the results to let's say something which could be called something like this title, without curve. But in consideration of the contents of today's talk, probably this would be too much. So I just put this. So I have some results already. Even before this about non-curve cases, but the class of those fractals is still limited. So I wouldn't. This title would be too strong. So so I just stick to this title. Okay. So. My main research topic is analysis of Laplace operators and Brownian motions of fractals. And the most typical and classical kind of fractals are these exactly self-similar kind of fractals. Okay, so this is the famous Sierpinski gasket and carpet. And for this kind of exactly self-similar kind of the analysis, the construction. Analysis of the Laplace operator and Brownian motion, in this kind of exact similarity, is date back to actually, almost 40 years ago. So there's already a history of 40 years for this one. But actually, in the some other field of mathematics, basically complex analysis and the theory of Euclidean groups, there are entirely different geometries of these topological spaces like these ones. Okay. So this one is called the Apollonian gasket. And by the way, since this one is being recorded, so these the pictures of these circle packing fractals are taken from this survey paper of mine. So please include this in the recording. Just for clarity. Okay. So so this fractal, called the Apollonian gasket, is constructed in this way. So here we have externally tangent, 3 circles in the plane, and you have some triangular region. And it's classical to see that there's a unique, inscribed disk in this triangular region. So let's remove the interior of that circle. Okay, and then you have 3 triangular regions of the same class, so you can repeat this operation, and we can repeat this operation indefinitely. And by taking the by considering what remains after the infinitely many steps, you get this fractal, and this is called the Apollonian gasket. Okay. Okay. And if you start with some different circles, then you get geometrically rather different pictures like this, or like this. Or like this. Okay, so they belong to the same class, but their particular geometries are rather different for each one. Okay, and since each triple of 3 positive numbers alpha, beta, and gamma specifies 1 Apollonian gasket. So let's write k alpha, beta, gamma for the Apollonian gasket with radii alpha, beta, and gamma. Okay, and here are some fractal properties of this. Okay, so so DAG denotes the Hausdorff dimension of this class of the fractals, which is independent of alpha, beta, and gamma, and it's known to be between 1.3 and 1.32 or something. Okay, but he gave a bit more estimate on this, and there are some numerical results by McMullen in late 90s. But it's not important for my purpose, so let me not mention. And at the value of the Hausdorff dimension, the value of the Hausdorff measure of this fractal is known to be positive and finite. Okay, so it's a well, decently nice measure. Okay, and well, okay. So the latter one, well, this one is topologically the same. Well, it's homeomorphic to the classical Sierpinski carpet, and well, I will briefly mention how how this fractal is constructed in some later this talk. Okay, and the problem I have been interested in and I have been studying in this context is to construct and analyze some suitable Laplace operator and Brownian motion, which kind of respect this given particular Euclidean geometry of the fractals. Okay, so as you see, these fractals in the right-hand side have entirely different geometries from these ones. So let's say once the geometry has been changed, probably the same Laplace operator wouldn't make much sense in the new geometry. So I'd like to answer what would be the suitable Laplace operator in the right-hand side. That's basically the question. Okay, and okay, so let's say to justify that this is a non-trivial interesting problem, let me just briefly recall how the construction of the Laplace operator here in the self-similar geometry goes. Just briefly. So this is this illustrates the construction of the Dirichlet form corresponding to the Brownian motion in the case of the Sierpinski gasket. So we consider this sequence of graph approximations of the Sierpinski gasket. Okay. And at each stage, we just consider the Dirichlet form given by the combinatorial graph energy. And after suitable rescaling of this one, in this particular case, it's given by this number. And then you can take the natural limit of this sequence of discrete energy. And the limit object is some nice energy functional, whose generator is what is called the Brownian motion on the Sierpinski gasket. Okay. But here, from this picture, it's this picture shows that let's say this construction assumes that the diffusion process should behave the same way everywhere and in every scale. No matter which scale and which position in each scale you choose, basically the behavior of the random walk is the same. So it really assumes that the behavior of the heat diffusion is everywhere, every scale is the same. Except for this scaling, of course. Okay? And the same is true also for the Sierpinski carpet. So this shows the initial construction of the Brownian motion Sierpinski carpet due to Barlow and Bass in 1989. So they considered the sequence of the reflecting Brownian motion on this sequence of approximating Euclidean domains in the plane. And at each domain, they considered some suitable scaling of the reflecting Brownian motion. And they show that this sequence has at least subsequential limits, which are non-trivial. So they are in this kind of way they constructed some limit diffusion on the Sierpinski carpet. And now it's known that actually this sequence with some slight adjustment of the scaling, now it's known to be convergent to a unique limit. Okay, and again in this picture, since the approximating sequence is just reflecting Brownian motion, the behavior of the diffusion is basically everywhere the same, and the local no matter which scale you choose, the local behavior of the diffusion is again chosen to be basically the same. Okay, and so but that kind of very homogeneous kind of nature of the diffusion process would probably not be very appropriate for this kind of situation, where depending on your location or in your fractal, the local geometry of your space can be very strongly distorted, right? And in this kind of situation, let's say assigning exactly the same resistance on each edge might not be very suitable, right? So, well, I was hoping to see that, well, probably there would be some more, well, suitable Laplace operators in this, well, right pictures, well, which is, well, more naturally connected to the given geometry. That, well, this is a question, okay? And my earlier results are basically this. So in this, well, right pictures, well, I have found, well, one candidate of some, well, natural, well, Laplace operator and corresponding Brownian motion. And, well, I have, well, okay, and I have, well, I did some analysis of the eigenvalue asymptotics of the Laplace operator in this case. Okay? So that's my earlier result. And, well, in the end of today's talk, well, I'd like to mention some a bit further progress, just a bit, but okay. So, okay, well, given this kind of class, well, okay. So the problem with, well, one obvious problem with this study is that the class of fractals is, well, limited to, well, circle packing fractals. Well, I will explain what the Laplace operators look like, but it does heavily depend on the circle packing structure of the fractal. So it doesn't extend at all to non-circle packing cases. And, okay, so, yeah, so I'd like to treat the case where your fractal consists of, well, non-rectifiable kind of curves, like the, well, topological Sierpinski carpet, but with, well, each boundary arcs, well, given by some quasi-circles or things like that. Okay, so so things like that. So yeah, some, well, so some deformation of this kind of fractal, well, in such a way that after the deformation, well, you have Sierpinski carpets whose, well, arcs are basically singular quasi-circles. Well, I would love to consider those kind of situations, but this seems to be difficult, and I have that succeeded. And as a preliminary step for possibly preliminary, well, preparatory kind of step for number 3, well, I have done something, well, for the case where your fractal is just a single quasi-circle or quasi-arc. Okay. So yeah, so I will talk about, well, this in the end of today's talk. Okay. And, well, what would be even more interesting, well, would be to consider something similar for, well, random self-conformal curves like, well, basically SLE type, well, fractals. So, well, okay, but the analog of 4 would be the case of the SLE curves, which are simple, so that with parameter kappa between 0 and 4, so that these curves are almost surely simple. Or there's a class of random fractals called the conformal loop ensemble carpet. So these are basically, well, topological Sierpinski carpets whose boundary arc, well, each look essentially like SLE kappa curves. Okay, and I am strongly interested in these cases, but yeah, well, I have absolutely no idea what could be done. So yeah, it's just a, well, possible future motivation. I don't know. Well, in, well, 1 decade or 2 decades, well, something might become possible. But at the moment, I have absolutely no idea. Anyway, let's start with, well, these circle packing cases. So in this case, the situation is somewhat clear. And okay, so yeah, so in this case, okay, so we start with the case of the Apollonian gasket. In this case, well, the first, well, construction of some nice Laplace operator was given, well, in this Teplaiev's paper. So, well, he proposed the following kind of constellation. So let's require that, well, your Dirichlet form, the energy functional corresponding to Laplace operator, to satisfy the following property. The two coordinate functions from your fractal to the plane, they were given by the values of the coordinate function. Well, they should become harmonic with respect to your constructed Dirichlet form. Okay? Well, meaning that after having constructed the Dirichlet form, well, this given geometry well, becomes a harmonic embedding of the fractal into the plane. Okay? And well, it kind of, well, okay, it certainly has some, well, natural meaning. So, well, the geometry is given, and, well, we construct Laplace operator so that, well, this geometry becomes a harmonic embedding into the plane. Okay? And Teplaiv proved in this paper that there is at least one such construction. Okay? So, well, he proved that there is at least one non-trivial, well, Dirichlet, well, local, well, diffusion type, well, symmetric Dirichlet form on the, well, this fractal. Okay? And okay, well, he just well showed that well, there's one such Dirichlet form by some abstract well, constellation, some abstract geometric constellation. And well, later I studied well this this particular case a bit further, and well, I have managed to prove that well, actually well, such a Dirichlet form is unique. Okay, well, okay, well, up to well, positive constant multiple of the form, of course. Okay. So to be very precise, actually, well, I haven't yet specified well which reference measure well is well to equip well this fractal with. I mean, well, the notion of Dirichlet form doesn't make sense without the without the reference measure on the state space. So to be precise, well, one should specify the choice of the reference measure on the state space. But at the stage of this statement, actually the choice of the reference measure on the state space is not important. Well, no matter what Dirichlet form well, you choose, well, okay, well, this property uniquely determines the core of the domain. I mean, the domain intersection the set of continuous functions, and the energy functional restricted to the set of functions in the core. Okay. So and well, okay, well, regardless of the choice of the measure, well, the subset of continuous functions, well, and the energy on that are uniquely determined. Okay. And moreover, in fact, well, this was a surprise to me actually. So, well, indeed, actually, this unique Dirichlet form is explicit and given by this one. Okay. Okay. So the set of Lipschitz functions on this fractal well form the core. So it's a dense set of functions in the domain. And on this core, this Dirichlet form is given explicitly by this sum. Okay. So the sum is over the set of the arcs constituting the Apollonian gasket. Okay. And well, the summand is well just the sum. Well, okay. Well, so well, each C is a circle, and well, circle in the plane, and along that circle, well, you just take the one-dimensional usual Dirichlet form, and well, here volume is just a length measure. Okay, and okay, well, without any normalization, well, this might diverge, but well, we multiply this by the radius of the circle C, and then actually, well, this well is going to be always convergent for Lipschitz functions. Okay, and okay, well, in view of this expression of the energy functional, well, this formula suggests the natural choice of the reference measure on the space. Okay, well, that is well just the okay, well, in typical situations, the value of the energy is given by the integral of the energy density function. Okay, and here the energy functional is already given by this kind of integral of the energy density. So well, if you forget the part of the energy density, then you should get a natural measure. So yeah, in this situation, the natural choice of the energy of the reference measure should be just this part without this energy density part. Okay, so that the choice of the reference measure should be this one in this case. Okay. So just the radius, the range of the summation is the same, and we just sum up the radius times the one-dimensional length measure. Okay. This this expression might look a bit mysterious, but actually, it's not very much actually. So, suppose this part, this is some part of the arc in, or the part of the, some part of one of the arcs C in the Apollonian gasket. Then its measure under this reference measure is actually given by twice the area of this, this sector region. Okay, so it's supported on this arc, but its quantitative behavior is kind of two-dimensional in this kind of way. Okay, and since these sector regions are mutually disjoint, the sum of these measures is just becomes the area of triangle like this, which is finite. Okay, so this indeed defines a finite measure with full support. Okay, okay, so in this way, some seemingly canonical Dirichlet form has been obtained for the Apollonian gasket. Okay, so the energy functional is this one, and the reference measure is this one. So the generator can be defined through them. Okay. Yeah, and okay, one more remark is actually, this expression is basically the case where this density part is 1, or in other words, if you sum the energy coming from the x coordinate and the energy coming from the y coordinate, okay, so here this one denotes the measure given by forgetting this integral sign. Okay, and if you sum up these two measures associated with the coordinate functions, then you recover this reference measure. Okay, so this could be considered as the energy measure of the embedding mark. Okay, that's another way of looking at this. Okay, and for the Laplace operator defined in this way, I have managed to prove this result. So for each alpha, beta, gamma, you have a Laplace operator, and it's easy to see that the Laplace operator has compact resolvent or discrete spectrum. So we can consider the sequence, the increasing sequence of its eigenvalues. Okay, and let's consider the so-called eigenvalue counting function, which is the number of eigenvalues less than or equal to lambda. Okay, then it turns out that it grows like the lambda to the Hausdorff dimension over 2. Okay, and what you see in the limit is some constant independent of alpha, beta, gamma times the value of the Hausdorff measure of the fractal. Okay, so the usual kind of Weyl's law for the eigenvalue asymptotics is true in this case.
How about the multiplicity of this discrete eigenvalue?
I have no idea. I have never studied this. Yeah, that's usually a difficult question. Okay. So this is a result. These are the results for the Apollonian gasket. Okay, and here are some remarks. Okay, so okay, so basically what this explains what are different from the cases of smooth spaces. So the first comment is, in order to define as the volume measure on the state space, I have used something like the energy measure. Okay, and in the eigenvalue asymptotics, we see the Hausdorff measure. Okay, so whereas in the classical setting of smooth spaces, both of these two measures would be just some constant times the Riemannian volume measure. But in this case, these two measures are easily seen to be singular. Okay, it's clear because the energy measure is supported on the set of arcs, so it's supported on a set of one dimension. Whereas for the Hausdorff measure, well, since the Hausdorff dimension is known to be greater than 1, well, if you measure the set of arcs by the Hausdorff measure, then it's obviously 0 because the arcs have Hausdorff dimension 1, and the Hausdorff this value is greater than 1. So it's trivially 0. And well, this already shows this singularity. Okay? So we have two measures. Well, one for the defining the Laplace operator, and the other for the Hausdorff, the Hausdorff measure for the eigenvalue asymptotics, and they are mutually singular. And another comment is, well, actually, well, this is kind of multifractality of the behavior of the heat kernel. Okay, so yeah, so this kind of asymptotic behavior of the eigenvalue counting function is well known to be equivalent to the corresponding behavior of the trace of the heat semigroup, which is given by the Laplace Laplace transform of the counting function, or equivalently the diagonal integral of the heat kernel. Okay, so this asymptotic behavior is equivalent to the asymptotic behavior of this in this kind of way. Okay, so it's the same, it's equivalent. So after the space integral of this one, you get the Hausdorff dimension. But if you look at the asymptotic behavior of this heat kernel, then what you see is different. Okay, for energy almost every point, the behavior, the pointwise behavior of the diagonal of the heat kernel for very small t is actually t to the minus square root. T to the minus 1/2. So so pointwisely, almost everywhere at least, its behavior is one dimension as the since the this is because the Dirichlet form is basically locally one dimension. But after integrating out, this becomes the Hausdorff dimension. So before and after taking the integral, the order of the asymptotic behavior changes. So something like the multifractal analysis of this should also be done, but this might not be that easy, and I haven't yet tried. Okay. And I have extends this kind of consideration to some other classes of circle packing fractals. So far the classes are rather concrete. Just this one. The construction of this one is rather complicated, so let me just skip. And this is the same as the one in the second page. Okay. So So next, let me just briefly explain how this is constructed. Okay. So for this one, or also for this one, at least one candidate of the Dirichlet form is obviously given already. That's given by this formula. Okay. Given a circle packing fractal, this expression already makes sense from the beginning. Okay. So now for other circle packing fractals, we choose, I choose, this one as the definition of the reference measure and the Dirichlet form. Okay. So just to remind, the expression of the Dirichlet form is given by this one, and this is the reference measure. Okay. And at least for the Apollonian gasket, this was unique in this sense. So it would not be it would not be unnatural to consider such a Dirichlet form, I would think. Okay. So basically the circle packing structure allows us to construct the natural Dirichlet form and the reference measure in this kind of way. Okay. So the construction of the Dirichlet form is basically already over. Okay. And let me explain how this fractal itself is constructed. Okay. So actually, it's the minimal invariant set of some very classical kind of hyperbolic groups of Möbius transformations. Okay. So it starts with some hyperbolic geodesic triangle in the hyperbolic plane. Okay. So here, so this is the origin of the unit circle, and we have a geodesic triangle with angles pi over m and right angle and pi third. Okay. And then, well, since these three angles are all pi over integers, so that some elementary piece of the hyperbolic geometry applies, and the group generated by the reflections, hyperbolic reflections in these three lines, generates a tessellation group, so that the images of this hyperbolic triangle by the group generated by these three reflections tessellates the hyperbolic plane in this kind of manner. Okay. And now we add another circle with respect to which we will invert the whole picture. So that's this circle. Okay. So the center is here, the same origin, the origin, and we take a circle so that the angle here is pi third. Okay. So now again, it's the pi over some integer. Okay. So some similar elementary piece of hyperbolic geometry applies, and you can analyze this. Okay. And if you add to this tessellation group the reflection in this new circle S, you can obtain you have some group of maybe transformations, and you can generate some circle packing fractals in this way. So we start with this inversion circle S and the unit circle. And if you invert the unit circle by S, then you get this one. And then you have the tessellation group. So let's consider the image of this circle by the tessellation group. Then you get something like this. Okay? And you can invert further these new circles by S, and then you get this. And you can consider the translation of these by the tessellation group. Okay? And you keep doing the same things. Okay? In this kind of way, you get some more and more circles which are mutually disjoint. Okay? And after taking the union of all these circles and taking the closure, you get some topological self-infinite carpet, which consists of round circles. Okay? Okay? Okay, and this case is the m equal 8, m equal 9 is this, and this is for m equal 12. Okay, and actually this group, and especially the case of m being 12, is a very well-known kind of hyperbolic group of maybe transformations. Okay, so it's some another piece of elementary hyperbolic geometry tells us that this group doesn't contain any parabolic elements, so that it's a Gromov hyperbolic group actually. And this fractal, this invariant state, can be naturally identified with the Gromov boundary of the boundary at infinity as a Gromov hyperbolic group. Okay, and fractal geometric properties of this fractal is very nice. Actually, it's alphos regular with Hausdorff dimension strictly between 1 and 2. Okay, and if you consider the I have already defined the Laplace operator, so let's consider the eigenvalues. For but to be a bit more precise, I have to consider an open subset U, which has strictly positive distance from the unit circle. For some technical reason, I have to do that. But besides that, we can do the same. We can consider the Laplace operator and consider the same thing. And I have obtained the same kind of result for the asymptotic behavior of the eigenvalues in this kind of manner. Okay, so the limit is proportional to the value of the Hausdorff measure of the domain again. Okay, so this is the result for the this case. Okay. Okay, and so up to this stage, the class of fractals were limited to circle packings, and the reason is obvious. The formula for the Dirichlet form doesn't make sense for the other classes. Okay, but still, typically, self-conformal fractals appearing in the complex dynamics, typically consists of non-rectifiable curves rather than circle packings. So one should definitely study the case where the curves are non-rectifiable. And I'd like to study that kind of case. And So yeah, and indeed, by using some pieces of Teichmüller theory, you can indeed deform the you can consider some deformation of this limit set, so that after the deformation, you have some groups consisting of Möbius transformations whose minimal invariant set actually consists of is a self-infinite carpet consisting of quasi-circles. Such a construction is known to be possible, but this case seems to be a bit difficult. At the moment this seems still difficult. Okay, and as a primary, hopefully as a preparation. As a preparatory step for the 3, I have studied the case of self-conformal arcs. Okay, and the cases of SLE and CLE are far-reaching. Okay, so so in the remaining 10, 11 minutes or something, let me state the let me explain some a bit more some details of the case of the self-conformal arcs. Okay, so this handwritten picture illustrates the setting. Okay, so suppose we are given a Jordan domain U in the plane. Okay, and my fractal is some part of the this Jordan domain. Okay, some closed subarc of the Jordan domain, and it can be the whole. It can be the whole of the domain, the whole of the boundary, but it can be some part, just of some part, some connected part of the boundary. Okay, and we assume that it's self-conformal in the following way. Okay, so the arc from this one up to this one represents the fractal curve partial, and suppose we assume that this curve is divided into finitely many pieces, partial 1, partial 2 to partial n. Okay, and we assume that there is some expanding conformal map defined on a neighborhood of each of these sub-pieces. Okay, so that if you map this part by this conformal map, then the image of the boundary curve itself is given by some union of some other sections of the boundary curve. Okay, and this conformal map is required to map the part internal to the domain to the internal to the interior of the domain, and the boundary part to the boundary. Okay, that's a requirement. Okay, so the same kind of structure is assumed for each of these n sections. Okay, and another requirement is that this family of expanding map is basically ergodic. Okay, so in order to guarantee that we require this family of conformal map to be topologically the action of these families on the curve is topologically mixing on our fractal curve. In the sense that for any non-empty open subset, eventually occupies the whole of the curve partial after some number of operations of these expanding maps. Okay. Okay, so this is the setting, and it's also some classical facts in the complex dynamics that various self-conformal curves appearing in the complex dynamics indeed satisfy this structure. Okay, so one most classical example is probably this due to Bowen. So actually, this paper is this 79 paper is a famous paper about the Hausdorff dimension of the quadratic circles, which was published in the IHES publication. Okay, so in this paper of his, he gave some particular way of constructing such cellular decomposition. Okay, so the setting is he considers the invariant set of the discrete groups of Möbius transformation in the case where the invariant set is given by Jordan curves, closed Jordan curves. Okay, yeah, and he showed he gave a particular way of this kind of cellular decomposition of the Jordan curve. Okay, and some other situations can also be considered. Like for example, if you consider this quadratic polynomial z squared plus c, for c whose absolute value is sufficiently small, its Julia set is well known to be a quadratic circle. And for this kind of Julia sets, again satisfy this kind of structure. Okay. And now, for this kind of classes of fractals, I need to construct some suitable some suitable Laplace operator which respects the geometry in a nice way. And what I do is to first to use the harmonic measure on this curve defined from the inside of this domain U to define the Dirichlet form, or in other words, the values of the resistance on these curves. Okay. Since we are concerned with the situation where your fractal curve has some nice conformal structure, so since the harmonic measure is conformally invariant object, so I hope this doesn't sound unnatural at least to choose such a measure in defining the Dirichlet form. Okay. So this is the harmonic measure on the domain U from some fixed point Q0 in the domain. Okay. And I'm considering here functions U and V on the curve which are absolutely continuous with respect to the harmonic measure. And I'm integrating the products of the densities of these functions to define natural, one-dimensional Dirichlet form under these coordinate functions. Okay. Okay. But for the maybe what is more involved, what important is this. Okay. So if you this is the energy functional. But in order to define some Laplace operator, I still have to introduce a reference measure on the curve. And if I chose the reference measure to be just the same one, this one, then what you would obtain would be just the usual one-dimensional Brownian motion in the with the scale function given by this harmonic measure. So in a sense, that object might be respecting the geometry, but it's just a one-dimensional Brownian motion and nothing is new. So it's just meaningless to study. Okay. So instead, I consider something like the following. Okay. So remember that in the previous case of the Apollonian gasket, the reference measure has the meaning that it was given by the it had an interpretation that this measure was given by the energy of the embedding map into the plane. Okay, so I'm trying to do some similar construction. So I'm trying to construct some measure which looks like the energy measure of the embedding map. Okay, so the actual construction is this. So so in this formula, if you consider anyway, so if this power here were 2, is 2, then this would be just the distance squared divided by the value of the resistance. So this means if this power is really 2, then this value is exactly the the value of the energy coming of the embedding coming from the section of the curve from x to y. Okay, and but that quantity may diverge when the fractal curve is non-rectifiable. Okay, and in order for such a quantity to make sense as a measure, for non-rectifiable curve, you typically have to raise this quantity not to the 2 but to some higher power. Okay, in this way, and one can show that there exists a unique power so that this quantity actually defines a nice measure on the state space. Okay, so this is a replacement for the energy measure of the embedding map. Okay, and I have to stop soon. And for simplicity, and we are not concerned. We are not interested in the case of the smooth curves. So let's assume that the Hausdorff dimension is greater than 1. And this turns out to be equivalent to saying that this exponent here is strictly greater than 2. And okay, now I have defined the Dirichlet form and the reference measure, so we can define Laplacian. And the result is that under some nonlinearity condition on your fractal curve, you can still show this kind of values asymptotic behavior. And here, the nonlinearity of this curve means that as a similar set, the system is not conjugate to the system where each self map is given by conformal linear maps. Okay, and actually I must say that for these two examples, verifying this nonlinearity condition doesn't seem that trivial, and I must confess that I haven't just checked that the nonlinearity is indeed true in these examples. So that's still to be checked. Okay, although the case of the group of maybe transformations, probably this condition shouldn't be that difficult to verify. I think that should be manageable. But for the second case of the Julia sets, we have to consider here general conformal maps. And in this case, verifying this nonlinearity rigorously might not be that easy. Okay, I stop here. Thank you very much.
Thank you very much, Naotaka. Questions, comments? Yes.
Just about the coefficients before this 1 over square root of t in the diagonal sum of the head.
Yes. Sorry. This one.
Yes, you have explicit expression for this x and tx.
You can give. I can give some very crude estimate. That's possible. Okay. But for example, I haven't tried to show that the ratio converge. For example, I would suspect it does. It would, but as t goes to 0. I mean, square root of t times this. Would probably converge, but I haven't just checked.
I suspect that they are connected to the geometry of your. It's like H coefficients. Something like that. So as I'm asking.
Thank
you.
Yes. Also related to this slide, that once you have the expansion of the heat trace, you can do the determinants. Right. You do the
okay. This expansion is extremely weak in various senses. This is just almost everywhere, and this constant is very, very dependent on each x. And if you consider sets outside of this full set measure, then probably some different order would appear.
No, I mean the form above you have the trace of.
You mean? Okay, this one. Okay, for this asymptotic behavior, I have no remainder estimate. So, I mean, what I have proved is exactly just this one. And in order to consider the, let's say, so the yeah, yes, well, some more analysis. Well, so you are thinking about something like something like taking the residue of the corresponding zeta function, things like that, right? Yeah, I mean, let's say, I mean, it's not at all clear whether one could even extend the zeta function metamorphically, outside of the canonical region. So, yeah, and without any reminder estimate for this asymptotic behavior, that kind of consideration would not be possible. So,
more questions?
Another one, if possible.
Yes, please.
For the Mandelbrot set.
Okay. You mean the boundary of the Mandelbrot set? I have no idea. Yeah, it should be extremely difficult. Yeah.
Okay, more questions? Okay, if not, let's thank Naotaka.